Hello everyone, this is Rui PCB, your trusted PCB partner. Today, our topic is the analog ground and digital ground in 6-layer boards and why they cannot be treated as the same. In today's electronic products, we often encounter mixed signal PCBs, such as a system that has both high-speed digital processors and sensitive analog sensors or audio circuits. In this situation, a seemingly simple but actually crucial question arises before us. Why can't analog ground and digital ground be treated as the same? Today we will uncover the necessity of keeping them separate. Let's look at the PCB we're showing today. It's a high-speed one. From the 3D view, you can see that the center is a high-speed processor, on the right is a high-speed AD, and there's also a 1.2. You can see that its traces are all done with differential and length-matched routing, which shows that this circuit operates at a very high speed. Moreover, you can clearly see here a pure connection line, and the D on the left and right are separated. Where do the challenges of mixed signal PCBs lie? What is a mixed signal system? A mixed signal system refers to a circuit board where both digital and analog circuits coexist. For example, on our actual PCB, the left area is high-speed digital circuitry, while the right area is high-speed analog circuitry. The core of their challenge is the problems they cause. First of all, digital circuits generate transient switching currents during high-speed switching, which lead to ground bounce and power supply noise. These noises are broadband, high frequency, and can have large amplitudes. Secondly, there is the sensitivity of analog circuits. Analog circuits, especially high precision ones, are extremely sensitive to any form of noise. Even noise as small as a few tens of millivolts or even just a few millivolts can have a serious impact. Finally, there is mutual contamination. If digital circuits pollute the analog ground or analog power supply, it's like dropping ink into clear water. The analog signal will be drowned out or distorted. Let's also look at a real example. The red signal here is the analog signal we want, while the blue represents a contaminated signal. What we actually receive is the blue signal. You can see that the blue signal has many sudden high voltage spikes, which makes it impossible to properly interpret the signal we need. Why must analog and digital circuits be separate? This is why in mixed signal PCBs, we often need to separate analog and digital grounds. The main reason for this separation is to isolate noise. First of all, it's to prevent ground noise from affecting the analog circuit. The large current switching in digital circuits causes instantaneous voltage fluctuations on the digital ground plane, which is known as ground bounce. If the grounds are not separated, this ground noise will directly couple into the analog ground, raising the reference voltage of the analog circuit and causing the analog signal to be lost. In other words, the ground of the analog signal will already be fluctuating. The output signal is referenced to the ground, so any fluctuation in the ground will inevitably cause the output to fluctuate as well. Secondly, it's to prevent the conduction of digital noise. By physically isolating the analog ground and digital ground, we can effectively prevent high frequency noise generated by digital switching from being conducted through the ground plane to the sensitive analog circuits. Digital signals, as we can see, are actually composed of many high frequency components, which can be very disruptive to analog circuits. Lastly, it's about creating a clean base for the analog circuit, a relatively pure, noise-free environment to ensure its performance is not affected by the digital section. So what happens if we don't separate them? First, analog performance will degrade. ADC and DAC conversion accuracy will decrease, audio quality will worsen, and sensor outputs will become unstable. For example, in our analog circuit, the minimum ADC output resolution might be 0.1 volts or 0.1 milliamps. But if the noise level has already reached 5 milliamps, then the 0.1 milliamp ADC output resolution becomes meaningless because the noise itself is 5 milliamps. So even if the output is 0.1, it could actually be 5.1 or 4.9, which greatly reduces the accuracy of the ADC. Next, there are system function abnormalities. Analog voltage reference interference can cause the system to operate unstably or result in inexplicable errors. This is easy to understand, especially when it comes to signal transmission. If the noise is significant during analog signal transmission, the received signal may become impossible to properly interpret, which means the system functions cannot work correctly. Then there are EMC issues. Noise spreading within the PCB can lead to excessive EMI, making it impossible to pass EMC certification. For example, in our case, there are two transmitting ends. So if digital noise is significant and enters the transmitting end, that can lead to uncontrollable transmission signals, making it very difficult to pass EMI and DMC tests. Finally, there's the nightmare for engineers. Mixed signal noise issues are often sporadic, hard to pinpoint, and time-consuming to resolve. For example, when you detect noise in an analog signal and try to trace its source, it can be extremely difficult to determine where the noise is coming from. So how can we lay the groundwork for this kind of separation on a 6-layer board? A 6-layer PCB provides more ground planes than a 4-layer board, offering a better foundation for separating analog and digital ground. First of all, you can have multiple ground planes. A 6-layer board usually has at least 2 ground planes, such as layer 2 and layer 5. This gives us flexibility in our design. We can consider dedicating one of them or a portion of it specifically for analog ground. For example, in this computer, we can see its 2nd and 5th layers. Here are 2 ground layers. This is our power distribution structure. You can see that on the 5th layer, a specific area is designated for analog ground, and on the top layer, there is also a dedicated analog ground area. Having more layers and ground planes provides greater flexibility and allows for more effective isolation of different regions. Today we learned about the challenges of mixed signal PCB design and why it is essential to separate analog and digital grounds to prevent digital noise from contaminating analog circuits. This is key to ensuring the performance and reliability of mixed signal systems. In the next video, we will specifically explore how to achieve this separation on a 6-layer board and identify the most critical connection points to ensure effective isolation. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.